Test. Okay, good evening. Let's get started. So this is the last lectures. I just need to go through a couple examples on Stokes theorem, and then that concludes all the material. And then we can do a quick reviews, okay, just to see what are the important topics and see if you can jog your mind and where you stand and how much that you still remember, how much you used to study, should focus, okay. And we should also talk a little bit about a final exam. Here's a Stokes theorem. Okay, let's read it together. Let S be a smooth surface bounded by a curve C. Vector field F is continuous differentiable on this surface. Okay. And the surface integral formula is basically one side is a vector line integral and the other side is a surface integral. What it integrates, what it connects is, it gives you this so-called, basically the total circulation, okay, around the curve C. And then this side here, inside the integrand here, this is circulation density. So you're integrating circulation density over a curve C, and this is S with boundary C. So del cross F dot n hat give you the circulation density at a certain point on the surface S, okay, around a certain point. Okay. So that integration of circulation density essentially end up with a total circulation around the boundary of this surface S. And one thing that you have to be very careful is that the direction of the curve C, or some we call it orientation curve C, needs to be compatible with the orientation of the surface S. So in other words, the direction of curve C needs to be compatible with this n hat, which represents the orientation of the curve, the surface S, using the right-hand rule. So we demonstrated in the previous lecture. So the right-hand rule, there are two ways to use it. One way is to use your thumb representing the direction of C, using your index finger, okay, tangent to the surface S, and the middle finger gives you the n hat direction. Okay, so for the particular curve C, right, this will be this. So your middle finger relatively give you an orientation or direction for the n hat. That's how you will pick the n hat for calculating this surface integral. Essentially, next time you see a surface vector line integral, you can see, okay, instead of calculating vector, you can calculate the surface integral. And that's what the Stokes theorem is all about. Okay. Now, if I take a second examination of this formula for the Stokes theorem, okay, let's call it the columns here. So given a curve C, so let's say the curve C is in the 3D space and oriented this way. Okay. Technically, you can construct an infinite smooth surfaces with C as boundary. Okay, so by that we mean that, for example, if this is C over here, so you can draw something. Look, I can draw a surface S, call it S1, and this S1 has a boundary as curve C. And I can also draw another curve, another surface. Okay, let's call it S2. So S2 share the same boundary as S1. And you could also draw a curve, a different, and then a different one at the bottom here. Okay, let's call it S3. Right. All of these all has the same boundary, curve C. And technically can draw infinite surfaces. Okay. But what does that mean, right? If you go back to this surface integral, as the Stokes theorem, okay, if you go back to this Stokes theorem, and if you look at the right side and the left side, so left side we didn't change at all, right? The left side is still the same curve C, but the right side, according to what we just have done, technically you can use any one of the surfaces that you have drawn over here. So meaning it can be S1, it can be S2, as long as these surfaces share the same boundary, the curve C, then all of them's surface integral, right, or integration of circulation density on that surface will give you exactly the same vector line integral, which is the total circulation over the curve C. So this Stokes theorem essentially, right, the circulation density over the curve C, it does not depend on which surface, right? As long as the surface share the same boundary of this curve C. So that's an observation based on this Stokes theorem. This observation sometimes actually can enable you to select an easier surface. Okay, so I'll demonstrate through an example later. Okay. So let's take a look at an example. One more example on surface on Stokes theorem. So given vector field f equal to z, x, y, curve C as x squared plus y squared and equal to 1 counterclockwise. Surface S is z equal to 1 minus x squared minus y squared. Calculate this vector line integral using using Stokes theorem. Okay, so this is a typical question, right, for Stokes theorem. Okay. So you have the vector field, you have the curve C, and you have the orientation of the curve C. You also have a surface which has the boundary of the curve C. And you're asked to take a calculation of the vector line integral using Stokes theorem. And if you plot this, all of the information out, and C is a unit circle in the XY plane. Surface Z is a paraboloid pointing down, so downward, right, with a maximum at 1. So this is your surface S, Z equal to 1 minus x squared minus y squared. When Z equal to 0, the paraboloid intersect XY plane with this circle, same circle, right? X squared plus y squared equal 1. Okay, so now I'm calculating using Stokes theorem. Basically means you are calculating using this surface integral instead of using this vector line integral. You can take a look at the lecture notes how the vector line integral can be conducted. But in this case, I'm going to calculate this using the surface integral. Okay, so calculate surface integral needs to calculate this cross product or the curl. So you got the f over here. You just had to plug into the formula for this cross product or the curl. Okay, so you get, in this case, you get 1, 1, 1. And I need you to really pay attention to how this cross product is calculated. This is basically the first step you need for the surface. If you calculate this wrong, then the rest of the answer is all wrong, right? So it's critical. This is the first step. You have to get it right. A very common mistake, some student is sometimes they put a sign difference instead of positive, it become a negative, or negative become positive, right? That kind of mistake happens a lot in the exam setting. And next is to calculate n hat dA. Now, because it's a surface integral, so this is where you will actually look at the formula sheet. What kind of surface is this? And this is the surface is what we call explicit surface. Okay, it's not a spherical surface. It's not a cylindrical surface. It's an explicit surface, z equal to f of xy. So in that case, you use n hat dA formula for this type of surface. And the next thing is there's positive, negative. So in this case, you need to use the positive because C is oriented counterclockwise. So your n hat needs to be pointing upwards, okay, in this case. So n hat dA is negative fx, negative fy, and then 1 dx dy. Here's your function f representing this surface. So your f is 1 minus x squared minus y squared. The partial derivatives, two partial derivatives here give you negative, because you already got a negative. So negative partial derivative f over x is negative 2x. And then another negative, so you get just positive 2x. 2y, 1 dx dy. That's n hat dA. So now I'm ready to plug into this formula and here. And so s, so 2x, sorry, 1, 1, 1 dot 2x, 2y, 1 and dx dy. Okay, so this dot product gave me 2x plus 2y plus 1 dx dy. Okay, so your xy is determined, okay, this x and y limits should be determined by the shadow of the surface in the xy plane. And shadow of the surface in the surface is a circle. So from here, what do you think you should do? Should you straight ahead using Cartesian coordinates or polar, right? Because now you got a circle as the shadow. So for xy here, you need to change to polar, right? To change it to polar means x equal to a times, or radius times the x equal to, just a second here, a polar, yes, x equal to r times cosine theta, and y equal to r times sine theta, right, for double integral in polar coordinates. So you replace your x with r cosine theta, replace y with r sine theta, and dx dy r d theta. Okay. And limits for the r, right, is strictly based on the shadow or the circle. So r go from 0 to 1, that's the radius, and theta go from 0 to 2 pi, because it's a full circle. Okay. Okay, so that's basically the setting for this double integral. And then you just have to calculate each one of them separately. Calculate using r first and then theta. So I don't think there's anything tricky over here because the limits are all constant. Okay. And you're going to get a value of pi for this particular double integral. Right, so that gives you an alternative solution, not a solution, alternative method for calculating this vector line integral using this surface integral here. In the lecture notes, we do have a traditional way of calculating this vector line integral. You get exactly the same answer, basically. Okay, yeah. Now, one thing I want to comment on is, let's go back to these comments here, right? So if you look at these comments, remember what we said, is that when you have a curve C, you can have infinite number of surfaces sharing the same boundary. And you could select any one of the surfaces, okay, for the Stokes theorem. So now if I go back to this current question, okay, my surface selection for the surface integral is this current surface, which is what the question stated. Okay. So let me ask you a question now. So if we know we have infinite number of surfaces that have, as long as they share the same boundary, then you get the same answer. So what would be an alternative surface for this surface integral? What would be an alternative surface other than this one? Would you be able to just, you don't need to draw on a new surface, just based on this drawing right here, right? What will be another surface that you can actually use to calculate this surface integral, okay, to give you the same answer? Cylinder? I don't have a cylinder here. Yes? Negative Z. I need a surface. I need you to describe me a surface, not this S, but a surface. Yes. Yeah, the one. Yes. Sorry. Yeah. Yes. Yes. Exactly. The other surface is this one, right? It's a flat surface. So basically the S collapses into the XY plane or collapse into the circle enclosed by curve C, and that's a surface, alternative surface, okay? So you can certainly use this surface to calculate the surface integral, right? So if I call this as a surface, let's call this a surface S naught, okay? So what would you do? Let's see, S naught is surface which is x squared plus y squared equal to 1 and z equal to 0. Okay. So that's how you define S naught. Okay. And now you got your S naught. So basically your drawing, right, is like this now. Okay. So certainly but there's one thing I would disagree. You said Green's theorem. However, you cannot use Green's theorem. Do you know why you cannot use Green's theorem? So when you use Green's theorem, it's for 2D, right? 2D means what? The curve C is a 2D. And what else has to be 2D? Vector field also has to be 2D. Okay, so your vector field here is not a 2D, it's a 3D. So you still need to use Stokes theorem. So if I need to use Stokes theorem, then we're calculating this surface integral, and you already calculate del cross F. Okay, yeah. So what am I going to do is n hat dA? What kind of surface are we dealing with that here? So you have, remember the different cases, case 1, case 2, case 3. There's one case, look at the formula sheet. Where's my formula sheet? Over here, whenever you deal with surface integral, those are the formulas. So what type of surfaces we're dealing with here for the S naught? The plane, right? Exactly. This one, okay? This is how you would go to this formula sheet and you find, okay, so now my question would be, okay, so this is your surface now, and you know your plane, this is a plane Z equal to A, or in this case, A is 0, and you got two choices for the n hat, positive, negative, k hat. And based on the current phase orientation, your n hat must be k hat. And your dA must be dx, dy, right? Okay, so what do we got here? 111.001 dx dy. And what do we get? 1 dx dy S naught. So whenever you see this kind of integral, we basically that's dA over here. What does that give you? The area of this circle. And circle of the area is pi r squared, r is 1, so get into the pi, right? Same answer. Okay. So during exam, if you have the question specifically says, calculate this vector line integral using Stokes theorem with the surface S, and then you use the surface S, okay? Yeah. If the question did not specify anything, it just say, here's a curve, C, here's a surface, here's a vector line integral, for example. Just use Stokes theorem. So you could use that surface S naught. Okay, so you should end up with the same, simpler maybe computation and same answer though. Is that good? Yeah. Okay, so that pretty much concludes with the Stokes theorem. As you can see, for calculating Stokes theorem, one of the key is, right, once you identified the surface, then you need to rely back onto the surface typical surface integral, which surface that you have to use, and what are the n hat dA, okay, for that type of surface. Okay, so that's pretty much, that's it for the new contents. Now, Stokes theorem is a very important theorem, so it will be tested in the final exam. It's partly, although this is the last lecture, so it will be part of the final exam, right? And then also, as I'm going to review here, as you probably realize, I think I can point it out this in the previous lectures, or even from the first lecture of this class, is that the last couple of weeks of the lectures, okay, are really the highlight of the course. Now, there are many topics, okay, if you recall from the last lecture, last couple weeks, you know, you have a green theorem, you have a curl, you have a divergent theorem, Stokes theorem. So there are many things, basically surface integral also is part of the maybe part of the last couple weeks or 3 weeks, okay? So all of these things center around the last few weeks, but you know, when you come to the computation, right, they're not really new. They're everything that we have learned. They're more of application of the fundamental skills, the fundamental concepts. You integrate, you combine them together, and it present it to you as a new theory. Okay? So computation shouldn't be new, but it's the theories, it's the principles are new. Okay? So there are those topics, okay, certainly should be your focus for this course. Okay? So let me do a final review at here, just to give you a bigger picture, okay, of what we have learned. I do have a document with a little bit more detailed review information. I will post it on the Canvas. I probably already posted. But here I do a slightly different type of review, okay? Number one, in this course, we learned 3 types of integrals. And the first type of integral is double integral. I'll consider double integral and triple integral okay, I'll consider these two are falling into a similar categories. Okay. So when you're dealing with double integral and the triple integral, for double integral, you have Cartesian, and you also have polar. Right? So you have 2 choices, right? 2 different coordinate systems to use. For triple integral, you have 3 different coordinate system: Cartesian, cylindrical, and then spherical. So all of these are given in the formula sheets, and triple integral, double integral, right? Okay, yeah. So what you need to know is how to use them and how to find. The major part is how to find integral limits. So this is the key, because you had to find the linear limit and you can carry out the rest of the integrals. Use the concept, what we call the scan through the region, either the region R or region D. Right? How you scan really depends on your choice of coordinate system. So this is the first type of integrals. Another type of integral is what we learned is a surface integral. Right? This is very much different from your integrals of a single scalar function as you learned in your first year. A surface integral, the general formula is you have a vector field n hat dA. And then over here, you have 4 different choices: spherical, a cylindrical, a plane, and then a general z equal to f of x, y. Like what we just done, what we just done is, this is instead of this is f here, this is del cross f, right? But del cross f give you another vector field, so it's still vector field over here. Now, double surface integral, okay, could be considered as a double integral, okay, because once you simplified everything to the final few steps, like what we did, you look at the final steps here, basically it's a double integral here, right? So, but it started quite different, right? Doesn't look like as very different like a double integral, but you have a 2 integral signs, so literally it's a double integral. Okay? And the last type of integral is called the line integral. We have learned 2 different vector line integral, with 2 different line integrals. One is vector line integral, and the other one is a scalar line integral. Scalar line integral is the type of integral we learned prior to the midterm, okay? And the vector line integral is what recently we have learned. Okay? So when we learn the vector line integral, okay, it's the total circulation concept, okay, around C. So that's what the vector line integral we learned. There is another type, it's actually also called flux across a line integral, across a curve. So we didn't cover that. Okay? So that's all of these things is very much like the last maybe 4 or 5 weeks of the content, right? From vector line integral to double integral, triple integral, right? To the last of the surface integral or Stokes theorem. Okay? And then on top of this, okay, there are a few bridges, I would call it. So I call it connection bridges, okay, for the integrals. Okay. So we have a few theories that actually connects some of these integral concepts or action together. Okay. The two theories are exactly the things that we learned in the last week. So number one, it connects a double integral and the triple integral together. And this is called divergence theorem. And then there's, of course, there's a connection, right? So the surface S is a closed surface. And the region enclosed by this S is given by this D. The connection is that. So you look at the divergence theorem, and that's basically giving the formula sheet, giving over here. So if you integrate, if you get the flux, our flux of the surface S, it's equivalent to integrate the flux density within this region D, and you get a total flux, basically net flux out of this surface S. And second is what we just illustrated is the Stokes theorem. It connects a single line integral, vector line integral, with a surface integral. Right, so that's the Stokes theorem. So if I have to give you a really bigger picture, and basically after the midterm, and that's it. So the bigger picture after midterm, so let's zoom in a little bit here. Essentially, it's what listed over here. Less than 10 lines of writing, right? Double integral, triple integral, surface integral, line integral, divergence theorem, and then Stokes theorem. And of course, there's also the Green's theorem. Okay. I consider Green's theorem as a special case of Stokes theorem. Okay. So we can consider Green's theorem as a special case of Stokes theorem. Okay. Now, of course, in order to do any one of this, there are a number of important small concepts. Let's call it, okay, not trivial, right? It's small concepts, okay, fundamental concepts. So what are the concepts involved in any one of these calculations here? Dots and cross product. And you can literally see there's so many dot products. There's also cross products, right? So you need those scale to calculate. You need to know the formulas, and you do have the formula for cross product. Where are they? Right here. There's a cross product here, right? Yeah. And you also need the fundamental scale for calculating partial derivative, because all this divergence and curl, right, there's partial derivatives everywhere. So we're not going to test a question on partial derivatives, specifically on partial derivative, but you need to know how to do partial derivative, right, in order to calculate any one of these computations. And then there comes the three operators, right, that I have emphasized, right, again and again and again. Out of this class, okay, if the next instructor teaching you a different subject and wants to do review, so one thing you should confidently tell him what you learned from this course are the three things here. Okay, so what's gradient, what's curl, and what's a divergence. Okay, and what is the physical meaning for each one of these calculations? Okay, simple wording, you can describe that. And you can also see that many of the questions are based on certain line, certain plane. So give you a plane equation, or maybe sometimes give you a line equation, or parametric equation for a curve, okay? Or so these things, although, this is prior to, this is not part of the final exam, but do I need to know what the plane equation looks like? Yes, right? Do I need to know how to get the parametric equation for a simple circle centered around the origin? Yes, you do. How about a simple parametric equation for a straight line from point 1 to point 2? Okay. Let's say from 0, 0 to 1, 1. What is the parametric equation for that straight line? And we've done that many times. So you need to come up with the parametric equation and the corresponding range for the t. And so that's a skill you must have. And next, okay, we didn't have a chapter on surfaces, but we have lectures basically to demonstrate what are the typical surfaces look like, especially an explicit surface, z equal to f of xy. Now, I have demonstrated, for example, z equal to x squared plus y squared. This is a paraboloid, and z equal to root x squared plus y squared. And what does this represent? A cone, right? So that's what I need, my expectation. If the question does not sketch it for you, then you should know, okay, that's a cone, right? That's a sphere. And x squared plus y squared plus s squared equal to 1, that's a sphere. I'm sorry, this is not a sphere, this is a paraboloid. Right? Those are very simple surfaces, is my expectation that you need to be able to know, okay? And sketch that very quickly. And the last bit of information or skill, which is probably not really part of this course, is that you do need to have the fundamental skills for calculating integrals, okay? Integral technique. And I don't expect you have a very complicated integrals. Sometimes very straightforward. You don't need to apply any technique at all. Most probably you have maybe a substitution involved. We have done that so many times. You have a sine cosine substitution, right? Or maybe a slightly different version. So there are many other different integral techniques. I don't think that's not my intention to challenge you in an exam setting, right? And to challenge you using integral techniques. The very basic ones is my expectation. Okay. So in the formula sheet, you do have some trig identities. Okay. Very typical trig identity. Let me see. It's right listed over here. Okay. So although in my opinion, they should be memorized, but you may or may not need it, right? So if somehow you need it, then you can use it. It's also some numbers, commonly used numbers from unicycle. So overall, right, you can see the big, really bigger picture, okay? It's all listed over here. Of course, there's some detailed level of knowledge, for example, gradient, directional derivative, right? So I didn't list it here. So you need to know that too, right? So whenever we talk about gradient, directional derivative, they are very much similar to you. There's also concept on, there's also concept on the constraint and unconstrained problem. Okay. So fortunately, you do have the formulas given, but the question you need to ask yourself is, where is that? Over here, yeah. Okay, so there's two parts here. Okay. Is how to use that properly. Okay, and if you have a constraint problem, you have to set up two equations to solve for the critical points, right? Okay, so I won't spend too much time at here. I think there's no way for me to reteach everything right, in the review here, but the review serve as more of as a reminder to you. You look at this one here. If you're presented with a formula and the approach to solve that question immediately jump to your mind, so I think you should be confident. Okay, then you're confident you know how to do with that question. But if a certain subject, and when you look at it, it comes a little bit blurry or blank, then that's where you probably had to go back to lecture notes or videos or assignments just to reinforce on that type of question, right? Okay. So I'll stop here, but regarding the final, okay, I know there are some questions as to like how many questions do you have final? We have 2.5 hours. So I expect that maybe 5 questions. So average about 30 minutes for each question. Of course, some question you will spend less than 30 minutes probably, okay? Yeah. 5 questions, I won't tell you what question on each category, but when you review, if you're smart enough, you should probably list the big topics, right? So okay, here's a big topic, double integral, triple integral, like what I listed here, Stokes theorem, divergence theorem, okay? So there's a higher chance, you have probably a question coming out of that category, right? Yeah. And also you have to be very, very careful when you do some of the computation, as I reminded, some questions, depending on your first step of calculation, like the cross product, del cross F. So that kind of a detailed level of carefulness will determine how well you go, right, in that question. So I have seen many examples, some student end up with a mistake in the first step, but the rest of the steps are all correct. This techniques all wrong, even though it's all correct based on the first step, the wrong answer. You probably won't be punished as severe as someone who doesn't know the question, but still, right? And you don't want that happen. For the final, I will provide the formula sheet, which is basically this one over here, okay? And I'll also provide scratch paper, okay? Now, also there are people asking, do you provide a sample exam? That's really not my style to provide a sample exam, because to be honest, when you provide a sample exam, it sometimes can be misleading. But my expectation to you is very straightforward. My exam question will be always similar or even same type of question as you exercise in assignments. If you do all the assignments, I can 100% guarantee that none of the exam question will be nothing you have seen before, okay? So my expectation is you do the assignments, okay, and you exercise. There are 2 VAP work assignments. There are a few traditional assignments that we have done in the previous year. There are also some additional exercise posted on Canvas, okay? I don't have a full answers for the additional exercise, but did posted some answers from prior students, also from one of the TA. Okay, so use this as a reference check, as a confidence booster, right? You pick a question, you say, okay, can I do this question? Pretend you never done it, right? Can you do it within 30 minutes? If you've done it within 15 minutes, boom, you're done. You should be confident in the subjects. Okay, so you can move ahead. All right. So don't trick yourself too much. I told the other instructor too. Okay, my intention is never to challenge you with some really trick ones. Is to test whether you have a good grasp of the concept you learned from this class. Okay, that's my intention. Let me see. Comments from the comment. Okay, so never mind. Anyway, now one of the TA, Hiba, she's very eager to provide a review for all of you guys, and she's very good. So I probably set up a time either through a Zoom or maybe a book a room, but I'll put an announcement on Canvas. Okay, so we have a lot of time till our final exam. I'll see pick a time and date so that you don't have a final exam, and then we can do a review from her. For me and the other instructors, I will try my best to make myself available. Okay, you can always email me to come to my office to ask questions. I can also set up some Q&A type of sessions, either in my office or through the Zoom or book classroom. Okay, it doesn't matter. But the point is, I won't disappear, and you can certainly approach for question. Okay, yeah. Any other questions about the exams? All good. Okay. So come about 15 minutes early on the day of the exam so we can set it up and start at on time. Unfortunately, it's 2.5 hours, so it might be a little bit tight. So I want you to be able to solve any questions within half an hour. Okay, so that's a reminder. Okay, so it's a bit of a different from your quiz exercise. Okay. Again, thank you very much. You know, this is a Friday. It's not easy, but I see most of you guys have been sticking to this terrible hours for the whole term. And I really applaud for your actually, you know, courage to come to the office, to the classroom for in-person learning. So I really appreciate that. Okay, so we should continue that for term 2. Okay, yeah. All right, so good luck with your rest of the exams. Yeah, thank you.